Good afternoon, everyone, and welcome to this third session on civil engineering and renewable energy. We are scheduled to have 4 speakers today, but it looks like possibly we may just have 3. Our first speaker is Mr. Rathan Babu Aswa from Universitat Politécnica de Catalunya. Our second speaker will be Mr. Pedro Brito, and he is based in the Association for Development of Industrial Aerodynamics. Our third speaker is scheduled to be Dr. Francisco Jimenez from the University of Alberta. And our fourth speaker is to be Miss Anna Fechner from the University of Exeter. So without further ado, I'll introduce you to our first speaker, who is a PhD student in UPC Barcelona Tech in the Department of Physics, and he is going to present on an OpenFOAM setup for simulating thermal winds in a mountain/valley configuration. So over to you now, Mr. Rathan.
Yeah, thank you. So it's my pleasure. So let me share the screen. So I think you are able to see the slides here. Actually, I'm presenting it online. So is it fine? Yes.
Yes, we can see it.
Yeah, I need some small feedback whether I'm sharing the screen properly or not, actually. So I hope our technical team will be giving the input. Okay. So yeah. Good afternoon, everyone. So this is Radha. So my work is based on simulation of atmospheric boundary layer in the thermal wind using OpenFOAM in Universitat de Catalunya. My supervisors are like Adeline, Rojas, and Sergio. So basically, for the information of so survey, I've seen that. So there are other softwares to specially predict the wind speeds, okay, and see the atmospheric bond over the plains or mountainous areas, or any masses. Case study, so where I'm using
Mr. Rathan, sorry to interrupt you. The audio is quite difficult to hear. Could I suggest that maybe you turn off your camera to see if that will help with the connection?
Yeah. Is it fine now?
That's a little bit improved. Yeah, thank you.
Is it fine now?
Yes.
Yeah. So basically, there are certain applications. So it's like analysis of thermal winds in complex terrains, and wind resource prediction of sea and land breezes. So here, and even ventilating the cities. So these are some interesting examples of atmospheric boundary layer. So yeah, then after, like we have, so previous Stipersky has used a model where in which he has used a infinite long mountain, so where he has simulated a katabatic wind, and he has seen the feasibility of producing downslope winds with a higher temperature deficit. So the temperature deficit is nothing but the difference between the wall surface, the temperature difference between the wall and the free stream. So if it is more, you can see here, like you have the maximum velocity mode. Okay. So this is what we have. So the main objectives of my problem is like to analyze these thermal winds in mountainous areas using OpenFOAM. Okay. So then after we will validate the solver first of all, whether the OpenFOAM solver, whatever I'm using, whether it is feasible to solve these atmospheric bond layer problems or not. So that is one thing. Then after we have to check whether the initial conditions, whatever we are using, the boundary conditions and initial conditions, whatever being used for the problem, whether it is correct or not, to simulate the upslope, which is anabatic, and downslope for katabatic flows, and to check the effect of the domain height, in the sense like if we increase the domain height and if we increase the domain width, so what happens to the domain, that's what we had seen, and to simulate the diurnal cycle in mountain valley. So the 24-hour cycle simulation is being done even in this work. Okay. So first, the main hypothesis of the simulation is like, so this atmospheric boundary layer is driven by temperature gradient. So this has come from the bosonic approximation. So bosonic approximation with is taken for the Navier-Stokes equations, and the gas considered here is like Newtonian and perfect gas. So radiation effects, Coriolis force, all were taken negligible, and geostrophic wind velocity is 0. So, and one of the important thing is that, so you have the diffusion perpendicular to the slope, which is normal to the slope. Fine. So this for validating the turbulence model, we had taken a paper from, of Axelsen and Schumann. So Axelsen has validated his Schumann's model with higher order schemes. So his model is like he has taken a slope with a 3D slope with an angle of 10 degrees. Okay, so these are the dimensions: 1700 cross 600 cross 850. So for this, so we had used different turbulence models, so K epsilon and RNG K epsilon model. So here on the top surface, whether to use the slip wall boundary condition or the symmetry boundary condition, there was a dilemma actually. In some papers they had used the symmetry boundary conditions, and in some papers they had used the slip wall boundary condition. So like for ventilating the urban cities, they have used symmetry boundary conditions. For this kind of model, Axelsen model, they have used wall boundary condition. So therefore we had verified, first of all, which model would predict the results accurately. So when we have used the slip wall boundary condition, so you can see the error. So the error has come which is less than some 5%. So here you can see that on the right side, so with the slip wall boundary condition for RNG K epsilon model, so the error was little higher compared to K epsilon model. So approximately it's of 28% to 27%. So when we are comparing K epsilon turbulence model and RNG K epsilon model. So Axelsen model, so it's like 6th order convective scheme, and Schumann's model is 2nd order convective scheme. Okay, so this is one thing. And here you can see when we had used the symmetry boundary condition, so for the given turbulence model, so since we are going for the RANS, so Reynolds average Navier-Stokes equation, so this is our turbulence model, and in the RANS, so we need to choose whether K epsilon has to be used or RNG K epsilon has to be used. So given that, so we need to also verify which type of boundary condition has to be used, whether it is symmetry or whether it is wall boundary condition. So in the first, in the previous slide, we had seen that, okay, K epsilon model and slip wall boundary condition on the top surface has given good results. And then you compare this K epsilon model and the symmetry boundary condition on the top surface. So here you can see comparison of the 4 figures. So we had found that, so the error is less than 4% when you compare all these 4 things. So K epsilon model and K epsilon model with top surface as slip wall has given the good results. So this type of boundary condition has been chosen for our model. So this is my model geometry. So here you can see, so this is the domain, so which is of having 20-degree inclined slope. Fine. So here in the boundary conditions, you can see I have given wall for the mountain surface, though inclined one is the wall. So the remaining thing, you can see the lateral things are symmetry, and front and back. Since I am going for the 2D simulations in the OpenFOAM, when you need to go for 2D simulations, so 2 surfaces you need to make as empty. So front and back surface I have taken it as empty. So then after on the top surface I have applied as slip wall. Okay, so this is the zoomed view of mesh, so which has been done in the block mesh dig. Okay. So these are the boundary conditions. So basically, in order to simulate the anabatic flow, which is upslope flow, I have used temperature boundary condition where it is 288.15. So plus So this is the lapse rate. So 0.0045 into the height of the slope. Okay. So this is one thing. And on the in the internal field, so I have used 288.15 and on the flat surface I have used 288.15. So these were the boundary conditions were used to simulate the katabatic or the downslope flow. So I have taken the negative thing. Okay. So yeah, so first now we need to see whether the uniform pressure or non-uniform pressure initial condition has to be used. So when you compare, so when we compare the difference between uniform and non-uniform pressure, so basically here first of all we need to see whether the pressure given as an initial condition will affect the simulation or not. Why? Because in the bosonic approximation he has mentioned that the convection is predominant due to temperature gradient. So in the simulation, once we need to verify whether we are able to see any changes if we apply the pressure conditions as an initial condition. Okay, so when we have checked it, so there is actually the error is less than 1%. Fine. So this is the error. What do we have? So when you compare one with non-uniform slope, other with the uniform slope. So when we are seeing the Umax, so the value of maximum velocity on the mountain slope. So the error you can see it is okay. It has come 10 power. It has come less than 10 power minus 2. Okay. Yeah. So this is. Yeah, this is the modeled anabatic and katabatic flow. So the boundary condition. So you can see the vortex phenomena has formed near to the near to the mountain. Okay, so on the top of the mountain for the anabatic, for the katabatic flow at the foot of the mountain. So this is
Mr. Rathan, I just need to advise you that we have maybe 1 minute left before we need to take questions.
Yeah. So here you can see that effect of domain height. So as the domain height is being the domain height is being changed. So you can see that the change of atmospheric boundary layer is he's been done. So we had seen at what height there is no significant change on the Umax on the mountain slope. So that's what we had seen. And we finally found that so at h is equal to 2600, so it has given a good result when it compared with the literature. And similarly we had seen the flat length. So when we had seen the flat length, it has been done with 1648 meters. Okay, so here actually this is the diurnal cycle simulation which is being done. Okay. So here you can see the simulation. First, it is done with katabatic, so downslope motion. So after 12 hours, so you can see that so it goes to Umax, then the vortex pattern will be changing. Okay, if you go slowly, so the vortex pattern is being changed. So this diurnal cycle simulation is being done using OpenFOAM. Okay, so with the bosonic approximation. Fine. So sorry. Yeah, so for the conclusion, so basically what is being concluded is like K epsilon turbulence model with slip wall boundary condition on the top surface has been validated. Then after we had seen that a uniform pressure initial condition is being approved, and a 24 cycle simulation is been done using the sinusoidal behavior of the time. So basically we had used the sine graph with respect to time. So the temperature on the mountain slope is changing with the sinusoidal behavior. So with that, so the diurnal cycle simulation has been done. In the future work, we need to simulate for 3D valley and to see whether if we have higher velocities on the mountain slope, we need to see the feasibility and see the type of wind turbine to be used in the mountain valley. Okay. So with this, I conclude my presentation. So thank you for your valuable time. So if you have any queries, I will be here.
Thank you very much. That was a really excellent presentation. So we have 2 questions for you at this time.
Yeah.
And more are coming in, so we'll see how many we can get through. The first question is, what inlet and outlet conditions did you take?
So basically, I haven't taken any inlet and outlet. So here in the inlet velocity and outlet velocity, so there is nothing like that. So I have taken symmetry, and the top surface has wall, and the bottom also have wall. So due to temperature gradient, the flow is being circulated.
Excellent. Thank you very much. Next question then is, were the values of H and L determined provisionally? Or is there some special relationship?
So we had seen the length scales and velocity scales. So with that, we had seen actually taken care. So whether it has satisfied it or not.
Excellent. A further question: did you compare the sensitivity of your results with other turbulence models?
So basically in literature, so many people has used either RNG epsilon model or K epsilon model. So out of these two, there was a question that which one to be used. So these two turbulence models were best for us. So for our atmospheric bound layer problem. So out of these two, we had chosen K epsilon model.
Excellent. That's fantastic. So there's a couple of more questions for you, Rathan, but in the interest of time, we'll need to move on. So I would invite you to look at these questions and engage with those that have asked them in the online portal. And at this time, we'll move on to our second presenter. So our second speaker today is Mr. Pedro Brito. And he is a mechanical engineer from Coimbra in Portugal. He's a researcher at the Association for Development of Industrial Aerodynamics and a PhD student at the Department of Mechanical Engineering in the University of Coimbra. And today he's going to present to us a CFD study on Irwin probe flows using OpenFOAM. So over to you now, Pedro.
So, hello everyone, thank you for tuning in. It's a pleasure to be a presenter at the OpenFOAM Workshop 16. I hope that you can see clearly my presentation in full screen. And if so, let's begin. I will start first by explaining what an Irwin probe or Irwin sensor is after all, and what is it used for. Then I will illustrate the adopted numerical method for the simulations. And in the results, I will reveal the complex full field developed inside and around an Irwin sensor, which is still undisclosed in the literature. And then I will end the presentation with some brief remarks. So, for those who don't know, Irwin probe are a surface sensor that was invented by Dr. Peter Irwin in the 1980s. And they were created to gauge the wind speed at the distances of a few millimeters above the surface of wind tunnel models. So they are particularly useful in pedestrian wind level evaluations, for instance. As opposed to conventional wind sensors like pitot tubes and hot wire anemometers, Irwin probes feature some unique advantages, like, for instance, they are omnidirectional, meaning that they do not require alignment with the flow, since they are axisymmetric about this vertical axis. And furthermore, due to their tiny dimensions, as you see compared with millimetric paper and some grains of sand, they have very little intrusion into the flow. So this is the geometry of the Irwin probe in a drawing of a cut. As we see, it can be simply seen as the assembly of a cylindrical cavity flush to the model surface, and from within, an inner coaxial tube with smaller diameter protrudes the surface up to a distance of h, which is called the protrusion height. And what is the sensor output? Well, this sensor outputs a pressure difference, which is simply the difference between the pressure at the cavity walls, in a pressure tap located anywhere, and the pressure at the tip of the protrusion, of tubular protrusion. And its operation principle is like Preston tube type sensors, meaning that they relate a pressure difference to the skin friction velocity or the wind speed at the height of the protrusion, called the free end velocity or free end speed. And this is attained by calibration of equations F1 and F2. But in this work, we are not concerned with the determination of such equations. We just want to characterize the flow. So for the model in the present simulations, we make some assumptions. We neglect the wall thickness and we seal completely the sides and bottom of the cavity. And these are the full-scale dimensions. As we see, they are really tiny. The diameter of the protrusion just 1.5 millimeters, and the height of the protrusion is 2 millimeters. So moving on for the case study, we studied 3 distinct undisturbed wind speeds approaching the sensor, which were 1, 2, and 5 meters per second, which are characteristic wind speeds in internal testings. And this yields a diameter-based Reynolds numbers of 100, 200, and 500, respectively. But as we see in this image, a flat plate boundary layer like develops upstream of the sensor location. Hence, the Irwin probe is actually fully immersed in a boundary layer. So these undisturbed wind speeds are never reached anywhere along the height of the sensor. As such, we adopt instead Reynolds H, which is based on the free end velocity, UH, occurring about here, and the height of the protrusion. And with this transformation, we get Reynolds of 14, 40, and 451. Since the dynamics for these two cases, 1 and 2 meters per second, are very similar, we will only analyze the latter two. So we move on to the implementation in OpenFOAM. We used OpenFOAM version 7, and to construct the mesh, we did it exclusively with block mesh. This is the top view of the computational domain. Ratan, in the last work, showed us some domain with thousands of meters in distance and length. In here, we have just a few centimeters. The 24 blocks, each is divided in each quadrant has 6 other blocks, and around the sensor here we have 2 refinement grounds with a gradient in cell size. So this is the top view of the computational domain. Now for the side view of the computational domain, we see here the sensor, the model of the sensor. This is the ground surface, and this is the kind of inlet we described, which follows a von Karman profile. The blockage ratio, which is the frontal area of the protrusion divided by the area of the inlet patch, was less than 5%. And this is the resulting mesh, which is three-dimensional and has about 12 million hexagonal cells. We diagnosed the mesh quality with the check mesh utility, and the mesh appeared healthy in all aspects. We also ran some preliminary refinement studies to check for proper grid density, achieving this discretization. And for the simulations, we used the piezo algorithm implemented as PiezoFOAM, as we all know. As such, we limited the current number to less than 1 at all time steps, and we simulated a total of 10 flow through domain times, but only the last 5 were probed for averaging. Furthermore, the simulations were performed in laminar regime, that is, with turbulence switched off. But also for the greatest Reynolds H tested, we also perform a large eddy simulation with the whale turbulence model. But that proved not important because all the solutions ended up to converge for a steady state value. So no marked differences were found between laminar and large eddy simulation. So we move on to the results. Let's look first at the velocity field. And in these images, we compare the velocity field around the sensor model for the regimes of Reynolds H451 and Reynolds H40, which corresponds to 5 and 2 meters per second of undisturbed speed, respectively. So first, it is evident that besides being directed over the crest and around the sides, a part of the flow is also diverted down into the cavity, which forms a circulation inside it. So also we see that in the back face, due to that circulation, there is an attached upwash that runs up to the trailing edge of the tube. And we believe that this dynamic is most likely due to the pressure buildup in the front and the pressure deficit behind the protrusion. And we also see a marked difference between these two states, where this Reynolds is more than 10 times greater, is that the reattachment occurs much later in figure A. So this got us thinking about the wake dissimilarities. So we further analyzed with 3D streamlines, which were seeded at the protrusion mid-height. And now we can see that really the behavior is so different. In the higher Reynolds regime, it can be noted the appearance of a pair of counter-rotating vortices at nearly free end level that propagate in the streamwise direction. In the literature, these are commonly known as tip vortices, and they are characteristic of wall-mounted low aspect ratio obstacles. We believe that the appearance of these tip vortices is related with the separation from the sides of the flow and that interacts with the upwash motion that we talked about in the last slide. But for the smaller Reynolds number, that behavior is in existence. In fact, the flow resumes almost instantly its directional uniformity, and no coherent flow features were found. So this begs the question that perhaps there is a Reynolds threshold between these two orders of magnitude, above which the typical wake patterns of low aspect ratio wall-mounted obstacles arise in the wake of Irwin probes. And to better depict these tip vortices I'm talking about, we use the key criterion visualization technique, and we see that there are actually a pair of tip vortices, two pairs, one secondary and another primary. And the important thing to notice here is that the primary tip vortices extend far, far downstream of the sensor, more than 10 diameters. And we believe that this is responsible for aggravating mutual interference of neighboring sensors placed behind it. So that is our key finding about the velocity field. And we move on to the pressure field, and there are no great surprises here. As expected, we can clearly see in this plot that a pressure differential arises inside the sensor. This is the line for the tube, inner tube, this tube axis, and these lines correspond to this wall and this wall. And of course, the delta P, in this case, was evaluated to be around 4 Pascal, is this difference. One other conclusion that we have here is that the pressure distribution is also radially symmetrical. So the position of the pressure tap along the cavity can be made virtually anywhere. That's why we have even probes with such distinct constructions. We also tested for the sensitivity in the delta P signal with the depth of the cavity, but we found that if we reduce the depth of the cavity to half, the delta P will still remain the same. So the depth of the cavity is not a big issue. So I'm almost ending my presentation. These are the conclusions. So I would say that the main conclusion is that mutual interference is not only conditioned by the distance between the sensors, but it can also be conditioned by the Reynolds H magnitude, that is the flow conditions around the sensor, and that there must be a threshold somewhere within these two orders of magnitude, where the typical patterns of low aspect ratio wall-mounted obstacles arise in the wake of Irwin sensors. In that relates to the velocity, and relating to the pressure, we can say that pressure distribution inside the sensor is both axially and radially symmetrical, and that the pressure output is sort of independent of the depth of the sensor. So that was the presentation. Thank you so much for the attention, and I'm ready to answer some questions if you have.
That was fantastic. Thank you very much, Pedro. Really nice presentation and some lovely images. I see just one question here in the chat, and probably we don't have time for too many, but do remember that we can continue the conversation in the discussion forum. So if you feel that you didn't get to ask your question or you didn't have time, we can move over to that. So the question that I see here is whether you could give us some more details on the selections of time steps in your simulations.
Okay, so what I did not prescribe a time step. I manipulated with pimple foam to work like a piece of foam, in the sense that with pimple foam we can just say I want this current number to be the maximum, and I have number current equal always in figure to 1, and then the solver chooses the time step itself. But I can say it was a few months ago, but it was certainly a time step very small, like one. There's a time. I think it was 6 orders magnitude less than a second. So
okay.
Sorry if I cannot.
That's okay. Thank you very much. Perhaps Pedro and Yuxian, who had that question, perhaps you can talk more about it if needs be in the discussion forum. So once again, thank you, Pedro, very much. So our next speaker now will be Dr. Francisco Jimenez from the University of Alberta. And his presentation is on the simulation of an electrohydraulic discharge for sand remediation applications. So over to you now, Francisco.
Hello, everybody. Can everybody hear me and at least see my slides?
Yes, we can. Thank you.
Perfect. Thank you very much. First, I want to thank the organizing committee for giving us the opportunity to present our work in this conference. The objective of this talk is just to give a brief overview of the work we are doing in the University of Alberta, the Faculty of Physics, in collaboration with 3P technology. We are working with an electrohydraulic discharge, where we can define this type of discharges as an arc between two electrodes when at least one is submerged in liquid. Most of the times both are submerged in liquid. In industry, pulse discharges are favored, and given the wide range of geometries that we can find, there's no universal framework or a mathematical network framework to help us model the process. Some applications of this type of discharges are for the treatment of waste and contaminated water, materials processing, oil well stimulation, rock fragmentation, and some ultrasound sources. We can divide a typical discharge into three stages. The first is electrical breakdown, the dielectric breakdown in the process. There is still not consensus as to what are the basic mechanisms that are leading for the creation of these discharges in water and gases is well known, but in liquids is a little bit more complicated. The second stage is one breakdown has occurred, and we have a gas channel between the two electrodes. We have a sudden release of energy that creates a plasma, and that's where most of the energy is dissipated into the process. And finally, when the plasma has been fully dissipated, we have a steam bubble whose volume totally depends on the geometry of the chamber where the discharge is being done. And of course, the efficiency of the process mainly depends on how energy is dissipated. For example, in a typical discharge, you can have you have energy in the steam bubble, you have energy dissipated as radiation, and energy dissipated in a shock wave. So there is room to optimize the process by just changing some of the few parameters in a typical reactor. Before I describe a little bit more of our work or how we divide this process, I'll just go into the experiment that we did to measure the shock wave of the discharge. We use a lab scale model. In this case, it's a small cylindrical chamber, the diameter of with a diameter of 19.3 centimeters and a height of 15.8, with two spherical electrodes where we run the discharge, and we place two shock sensors at the walls of the chamber as depicted in the picture. The schematic of the experiment is very simple. We just have a high voltage circuit with a switching circuit. It's just basically a bank of capacitors that are connected through the reactor through a spark gap. We charge the capacitors with around 10 kilovolts for this experiment, and then just activate the spark discharge. And we monitor current and voltage using a Rogowski coil and a high voltage probe. And we use just a bench oscilloscope that is connected to a computer, and then we're just using a simple Python script to get the information of the discharge. One of the applications for that 3P technology is working on is in the treatment and the remediation of tailings that are the waste that we have in a typical oil sand operation. These tailings are a mixture of they come in a form of a slurry, and this is typically a mixture of clay, sand, water, some bitumen, and also some other sediments. This is one of the applications that our 3P is working on. The premise of the technique is straightforward, and you can see in this figure how it works. We just have two electrodes where we have the slurry mixture in the chamber, and we shoot the discharge and generate shock waves, and those shock waves are promoting physical and chemical reactions in the slurry that promotes material separation. Here you can see the simulated shock wave at 3 different times, where T0 is just basically when the discharge is coming, appears, and then at different times how the shock wave moves in the reactor. For the first stage, which is electrical breakdown, there's still not a theoretical framework that it's favored. There are of course 1 or 2 that are at the front of the others, but we can build simple models, reduced models, to help us do a simple study of how the electrode shape affects the streamer propagation. In this case, I'm showing a simple two-fluid model, a simple fluid model of a plasma that built in OpenFOAM, where given that the mean free path of electrons in a liquid is very, very small, we can, as a first approximation, ignore the solution for the electrons and then just concentrate into ionic species, which are coupled with Poisson solver. We can see the results of this very simple model. for 3 different electrodes. You may think that according to these results, that a pointy electrode is favored over the others, but we have the problem that these pointy electrodes or sharp electrodes will erode much faster. So in a typical industrial setup, that's not ideal, because that will require for an operator to go and change the electrode very, very constantly, and that's not ideal. We have room for improvement in terms of electrode shapes and materials that we are currently working on. Next, which is the topic of this presentation, is the creation of shock waves. Once the breakdown has occurred, we have a small, a thin ion channel in the form of a gas channel between the 2 electrodes, and that's when most of the energy is dissipated into the process. All the energy contained in the capacitor bank is dissipated in the form of a plasma between the channel, and we have a sudden expansion of the gas channel, and that's the one that is generated shock waves. In OpenFOAM, we tried different solvers, and we settled with 2-phase compressible solver. Here is just a simple 1D mesh, a study where we study the mesh size and what is the size that we will need to properly capture the pressure wave that it's coming from the gas channel. This is just a 1D case where we have at one end a symmetry plane. We have a small thin gas channel that we initialize at a high pressure, and then we just have water with we're using for this case the Tate equation that's the equation of state for water, and at the other end an absorbing boundary condition just to avoid for reflections. We can see that we determine that that's probably the best one of the values that of the mesh that are a good compromise between efficient accuracy and time of execution. It's around 0.1 millimeters. Next, the steam bubble. We're also doing some work on it. Here we have it validated against the well-known Gilmore model. We use a simple one-dimensional model with a spherical symmetry in OpenFOAM to compare it against the Gilmore model. We use a setup that is very similar to Koch's master model, master thesis, and also we have a simulator bubbles in more realistic geometries, and we are still working on this part of the process. So related to our work, we divided the plasma, the generation of shock waves into 2 stages. The first one is an early stage where the plasma is expanding. So for that, we use a very simple circuit model in which we treat the plasma as a time-dependent resistor, and we couple it with the parasitic inductances and resistance and the capacitance of the system. And we use just a simple ODE to describe the evolution of pressure and temperature and channel radius. These are the results for the simple circuit model. And what is important here is to look at the maximum pressure in the plasma channel, because this is maximum pressure is the one that we use in OpenFOAM as an initial condition. The system, the model in OpenFOAM is just an axisymmetrical model where we are taking advantage of the symmetry of the experimental setup. We place a couple of traces in the locations where the sensors are, and initialize the gas channel with the high pressure, and then let it evolve. You can really see the results of the simulation and we can really clearly see that at as early as 25 microseconds, we already have a lot of reflections in the chamber that are caused depending on the geometry.
Francisco, so sorry to cut across you. I just need to keep an eye on the time. We have just 15 minutes left in the overall session, and we have a fourth speaker. So could I give you maybe just 30 seconds to wrap up, and we'll need to move on then.
Okay, sure. Thank you. So here are the results of the experiment. What is important is to look at the slope of the pressure wave, because that determines the failure mode of the materials we're trying to work with. And this is a comparison with OpenFOAM. We clearly see that the OpenFOAM can capture the slope of the pressures as measured from the two sensors, and also the magnitude of the pressure. There is a little bit of differences after that, but we are working into explaining, and we have a couple of theories to explain why this is happening. As a conclusion, electrolytic discharges are complex to simulate. We are our proposed coupling strategy is good enough to capture the rising time of the experiments, but we still need a little bit more work on it. And finally, this is what we're working on next. And sorry for
that's great.
Time.
Thank you very much. Thank you very much, Francisco. I suggest that if people have questions, that they could connect with you in the discussion forum. So we'll move on now to our final speaker, Anna, who's a PhD student in the University of Exeter. And without further ado, I'll give you the floor now so that you can get your full 10 minutes of presentation. So
okay, great. Thank you very much. I assume you can see my slides.
I can, yep, that's great, thank you.
Great. So yeah, thanks for the introduction. I'm a PhD student at the University of Exeter, and today I'll present about my work, which is on wave interaction of a tension leg offshore wind turbine platform with a perforated outer cylinder that is represented by porous media.
Sorry to cut across you, Anna. The bandwidth is struggling a little bit. Could I suggest maybe that you would turn off your camera and see if that will help improve the audio?
Yeah, of course. Okay, so the presentation includes a brief introduction on the motivation and the project description, which I'm part of. There's some experimental investigations we did. Then the CFD modeling I've conducted, and some initial simulations and results on that. So since I'm a member of the Renewable Energy Group, we have one big project going on, which is about the improvement of the platform stability of floating wind turbines. It is clear that floating wind turbines have a lot of advantages. They are a renewable energy resource, and the big advantage is that they can access water depths larger than about 60 meters. And as I said, the platform stability is one key engineering challenge here. And we came up with the idea of applying an outer perforated shroud to use it as an energy dissipation mechanism, and to dampen the motion of the platform, and mainly also to reduce the loads on the mooring lines. So we did some experimental investigations on that, which is also for model validation reasons. And we've studied static structures in the form of vertical sheets and fixed cylinders to investigate various geometrical parameters such as hole spacings, thicknesses, and the radius of the perforations. And because we are collaborating with a Chinese university, we chose the tension leg platform as the platform type here. So you can see some photos and videos here. And my part of the project is to conduct CFD modeling on that. And in order to represent this perforated outer structure of the TLP, there are generally two options. The intuitive one is a microscopic approach, where the detailed geometry of this perforated shroud is resolved in detail, which requires a very fine mesh resolution and typically comes with a high computational demand. There is one alternative option where this structure can be represented by its macro scale effects. So the geometry is not resolved in detail, but its effect on the fluid is represented by a pressure drop resistance by means of its bulk effects. And because in our case, we are mainly interested in the global forces and the mean flow behavior, the macro scale approach is our choice, our method of choice, because it's computationally less expensive compared to the microscopic approach, but still overcomes limitations of simpler models based on potential flow theory. However, it's clear that this method comes with limitations, and a very detailed fluid flow behavior cannot be represented very accurately. So I'm using here the Reynolds average Navier-Stokes equations with the use of OpenFOAM's Interfoam application solver package in combination with the volume of fluid method in that case. And there exist wave modeling toolboxes, and I'm using one of those. That's Olaflow and IHFoam. Where the waves are generated based on common potential flow wave theory, and the wave input is prescribed via the velocity profiles and the free surface elevation at the inlet. And on the opposite side of the wave flume, active waves absorption is applied by means of static boundary conditions. So that's the toolbox I can use, and it's readily available. And in order to represent the perforated structure, momentum resistance source terms are applied to the momentum conservation equation. And this is typically done via the commonly known Darcy-Forchheimer law, where a linear, quadratic, and a transient term can be applied to the momentum equation. And here I'm using two solver libraries, one provided by Olaflow and IHFoam, and one by Waves2Foam. In the very specific case of flow across a thin perforated structure or sheet, which is characterized by small thickness and flow separation at the edges, the flow regime is very turbulent with large Reynolds numbers, but also the fluid flow is quickly homogenized before and after the sheet. So in that case, viscous friction and also transient losses can be neglected, and the effect of the structure on the fluid can be represented by a quadratic drag term. So I've chosen a model where the drag coefficient is represented or a function of the porosity only, so independent of any wave conditions. The porosity here is just the ratio of void area to total area. Yeah, for details, please see those references. And the first package was to simulate, the work package was to simulate wave interaction with the thin porous sheet and also with the thin bottom fixed perforated cylinder. Here are some illustrations of the numerical wave tank I've generated and some photos of the mesh resolution. Here it's clearly visible that the detailed structure is not resolved in detail, so no holes and no geometry, but porous media is applied that represents the cylinder here. Yeah, here you can see a video, and you can see that the flow enters the cylinder, and the force, the horizontal force on the structure is measured by means of a time series, and the wave elevation is measured at wave gauges around the structure. And these are just examples of a wave condition and the wave gauge in front of the cylinder. And yeah, the agreement between the numerical CFD results and the experimental results is pretty good here. And this was where the studies on the static structures, and now they've been extended to the moving TLP with outer perforated cylinder. Also here, the TLP that the cylinder is not represented in detail, but by means of a porous media and momentum resistance source again, because this capability is not already included in the dynamic mesh morphing library of OpenFOAM. I had to modify the solver to account for the force on the porous part of the structure. So therefore, the force on this porous part by means of a pressure drop difference is applied into the motion solver bits of the code. Therefore, some extra specifications in the dynamic mesh dict had to be applied. And currently, I'm in the process of validating this modified and custom solver for this simplified model of a TLP, because these are preliminary models. The geometry of the actual TLP has been simplified. As you can see, the three legs have been omitted and the motion of the structure has been constrained to surge motion only. In combination with that, the three mooring tendons are represented by horizontal linear spring. So this is the first simple model to keep the computational demand low, and also the mesh is relatively coarse here. And the initial results show that it gives good results in that cases. So in here we can see the surge motion results, and it's a comparison between the experimental results and the OpenFOAM's default solver, which does not account for the force on the porous structure part, and then the modified and custom solver. And the initial results clearly show that default custom solver cannot accurately replicate the surge motion of the TLP with the porous shroud, but the modified solver gives pretty good agreement with the experimental results for the initial wave conditions investigated. So yeah, this is work in progress, and the validation will be extended and improved now. So the conclusions here are basically that a macro scale approach for porosity representation can replicate the large scale effects of wave interaction within perforated structures, then that the used pressure drop model as a function of porosity only gives good results for all investigated regular wave conditions. And the initial simulations with the modified solver show that the proposed macro scale representation works also for dynamic structures. Yeah, these are the present conclusions. Thank you very much for your attention.
That's fantastic, Anna. Thank you very much. I see a couple of questions coming in here, and we may get cut off at the end of the session, but we'll give it a go. So the first question is, could you explain how you calculate the porous media coefficients?
Yeah, it's a function of porosity, and I've shown on the corresponding slide. It's a formulation proposed by Molin, and so it's this slide. Yeah, function of porosity, and in theory, this discharge coefficient delta is a function of the Kc number. But Mr. Tite and Mr. Hamlin showed that the influence is pretty small, so I've made this simplification of just using a constant discharge coefficient here.
Excellent. Yeah. And I've another question here. What was the configuration of the boundary conditions at the outlet? Did you have fixed pressure, fixed velocity?
Specifically for the pressure, yeah, so in general at the outlet there is this active wave absorption method, which applies the velocity profile of the used wave condition in the opposite direction. So kind of a cancelling out of the wave takes place there. So it's active measurement, and then the incoming wave velocity profile gets cancelled out by the profile in the opposite direction. And with the with the pressure, I think it's a fixed pressure outlet. Yeah.
Okay, that's fantastic, Anna. Thank you very much. And as we've just come up to 1 o'clock now, I'd like to thank all of our speakers and indeed our delegates for joining us here in the session. I hope you have enjoyed the conference to date, and I look forward to seeing you at some more of the sessions later today and indeed tomorrow. So thank you again and take care.